part D was to find the intervals where f of x is concave up or concave down. So we're going to check the concavity now, and that can be checked when we find the second derivative. So the second derivative would be e to the x multiplied by x minus 1. This is going to be a little bit more complicated. Plus e to the x multiplied by 1. So that is the product rule of the numerator, and that's multiplied by the denominator. And then we subtract the numerator sorry, that's the this 2x is the derivative of the denominator multiplied by the numerator. And that's going to be all over the denominator squared. Now I need to simplify this a little bit. So I'll expand this in, simplify here, so I've got e to the x times x minus e to the x plus e to the x. And this is all times x squared. And then minus 2x e to the x times x minus 1 all over x to the power 4. And negative e to the x plus e to the x, those cancel. I'll factor a few things out, or I'll simplify things a little bit here. So I'm going to have x cubed e to the x. So I multiply this x times this x squared to get x cubed e to the x. And then I've got negative 2x times x minus 1 e to the x all over x to the power 4. And I'll continue simplifying this a little bit. And so I'll factor out, what can I do? Factor out an x e to the x. And then I'll have x squared minus 2x plus 2 all over x to the power 4. And then just simplifying down one more step, we see that we can reduce that x and one of those. So that will be x cubed then. And so that means that we are left with, for our second derivative, e to the x multiplied by x squared minus 2x plus 2 all over x cubed. So concavity changes at inflection points. And inflection points, I'll use a bit of short form here. Inflection points occur when f double prime of x equals 0. And when you multiply both sides by x cubed, that disappears, so we're left with 0 equals e to the power x multiplied by x squared minus 2x plus 2. Again, e to the x is undefined when it's equal to 0. And we've got x squared minus 2x plus 2 equals 0. And so I'm going to see if there are any inflection points here. So I'll take a look at this, and I'm just going to check the discriminant first, just to see where are we? Okay, so we got negative 2 is the b, all squared, minus 4 times 1 times 2. And we see that that is 4 minus 8, which is less than 0. Therefore, there are no real roots of this. Therefore, there are no inflection points. So we can check the concavity. So now we know that the concavity is not going to be changing anywhere along the line. So what we can do is draw the sign diagram for the concavity. But in this case, the only line that we need is where the graph is undefined. And that is, as we found before, when x equals 0. So now we substitute a value less than 0 into the second derivative, and we see that it's negative to the left of 0, which means it's going to be concave down. And when we substitute a positive value into here, we see that it's positive when x is greater than 0, which means that the graph is going to be concave up to the right of that. And so now we have enough information, and my drawing of this is going to be very crude, so I apologize. It's probably a good idea if you were to draw it yourself to get a better look at it. So I'm just going to do a quick little sketch of this. So we know that we've got a local minimum, at 1 and e. And we know there's a vertical asymptote at x equals 0. And we also know that there's a horizontal asymptote at y equals 0. So we know that as the graph approaches the vertical asymptote from the right, that the graph is going to be increasing. Okay, so we saw that from the interval chart before. Or actually, what we saw was to the right of this, the graph is actually decreasing. So it's going to be coming down here. Here's the local minimum, and then it's going to be scooting off to infinity over to the right. And the graph is still decreasing, this time as it approaches the vertical asymptote from the left, as you can see from your interval chart, or the sign diagram for intervals of increasing and decreasing. And we know that the graph is approaching 0 from below as x gets really, really big, negative. And this also concurs with the concavity, which is negative, meaning concave down to the left of the vertical asymptote of 0, and it is concave up to the right of the vertical asymptote at x equals 0. Okay, and then just the last little bit, the equation of the tangent when x equals -1. So we know that, what part is this? Part E. So for a tangent, we know it's linear, so that means we need the gradient and a point. So I'll take the gradient function, substitute in x equals -1. And then calculate the gradient. As I work all this stuff out, it becomes 2 over e after a couple steps. When x equals -1, we substitute that into the original function to get what the y value is. And so we end up getting e to the -1 over -1. So the y value of the point of tangency is 1 over negative e. And so for the equation of the tangent, that's determined by y minus f of negative 1 over x minus negative 1. That equals the gradient of negative 2 over e. And then when I rearrange this, I get y equals negative 2 over e multiplied by x plus 1 minus 1 over e. And that would then be the equation of the tangent of this function at x equals 1, or negative 1. Okay, so that is bringing everything together from chapter 16. Here's a bit of practice to work on from section 16D, and here is some practice from the review sets from chapter 16. So please go ahead and work on those. Maybe take a look at a few of them at home, and then come into class tomorrow and work on them for the rest of them in class. So thank you for watching, and we'll see you in class.